take a look at the topics we're talking about today. Lots of different topics, actually. In lecture A, we're talking about histograms, which is a harder type of graph that you did learn about making a little bit in your reading. Sometimes you are going to be having to do some things that we don't have time to get to in class. Okay, and so I would expect you to learn it from the reading. Also, you can get help from the math lab. We're going to talk about describing distributions using appropriate kinds of words, terminology to describe what we see. Something called the 5-number summary, and also something called box plots, or also called box and whisker plots. Then lecture B, we're going to talk about computing and interpreting means and standard deviations, and have a little introduction to something called a normal distribution, or more precisely, to normal distributions. All right. Well, let's review quickly what we did last time. So we were looking at Minneapolis high temperatures from March 2014 and 2015. We saw, well, you didn't see, I'm telling you that the average high, the mean high in 2014 was 33.9 degrees Fahrenheit, whereas in 2015 the mean was higher, 45.3 degrees Fahrenheit. What does that mean? Well, it doesn't necessarily mean March 2015 was always warmer, or consistently warmer, or typically warmer even. Typically warmer might be the closest thing to the truth, though I talked about how there could be one day that was a real high outlier that caused the 2015 temperature, the mean temperature, to be higher. Okay, so it's not even necessarily typically warmer, though that might be the most common thing you could say is true. The point is, we don't know without looking at the data in other kinds of ways, without looking at graphs. Does it mean high temperatures of the course of the month were consistently near those values? No, not necessarily. They could have been, but not necessarily. Again, we have to look at the graph. What kind of information? We're missing context and graphical information. In particular, these data are described over time. There's a context. Data always comes with context, real-life data. And the context is, these are temperatures over a month in Minneapolis. And so there's a time element, there's a day of March. We can graph those high temperatures based on the day. These are called time series. And you can see the general upward trend. How do you interpret the averages in this picture? Well, the average again for 2014 was about 34 degrees, and for 2015 was about 45 degrees. 45 degrees, focusing on the red graph, 45 degrees is at about right here. Essentially, if you made a horizontal line at 45 degrees, the area under that horizontal line would be approximately the same as the area under the red graph. That's one way to try to visually estimate where that average value is. It is sort of in the middle, also, of those high temperatures as they go up and down during the month. For the blue graph, it was, I think, 34 or so, right about here. Same property, the area under that horizontal line would be approximately the same as the area under the blue graph. So you can try to visually estimate it. It's not a real easy thing to do, but you can give your best guess based on this picture. You can certainly see that 2015 is higher. And consistently higher again between about March 5th and about March 21st or so. We also talked about stem plots to see the distribution of these data. They have distributions. It's more than just the mean, which is a measure of central tendency. There's also spread. Again, you want to look at these stem and leaf plots, or stem plots for short, with your head sideways and sort of see a graph. That's the point of trying to line up these digits, is you're trying to see the distribution. In this one, you see a pretty clear bell shape, again with your head sideways. In the second one, for 2015, it's a little less clearly a bell shape, kind of. It certainly goes up and down. But you might say that there's sort of a bigger chunk that's higher. In this one, it's the 20s, 30s, and 40s that by far predominated. In this one, there's sort of a range, 30s, 40s, 50s, and 60s that had lots of highs in those ranges over 4 groups of 10. And the lower temperatures are kind of farther away from the center in this graph. Again, looking with your head sideways, you would say this is maybe slightly left skewed. Ignoring this peak right there, these lower temperatures are sort of further away from the center then that high temperature is from the center. And in this one, the low and the high are pretty close to being evenly spaced from the center. So this one is definitely pretty symmetric. That's a word you've used. Whereas this one, again, thinking of it sideways, might be slightly left skewed. You got the bulk of temperatures in the 30. That's kind of perhaps arguing against the overall left skew. So it's a little tricky to try to say that's a definite left skew, but I certainly think that the minimum temperature of 12 degrees is further to the left, smaller than the center, the mean, for example, of 45, than 70 is, I guess. Yeah. 45 minus 12 is 33. That would be the distance between the low value and the mean. And 70 minus 45 is 25. So yeah, based on those extremes, there's a little bit of a left skew. I'll talk more about that. I know I went over that kind of fast there. You can generate stem plots at this website. And if you need to in the future, starting especially in chapter 7, go ahead and use the website. It's not too hard to draw by hand as well. Our most common measure of spread is called the sample standard deviation. We will talk about how to compute it by hand, so to speak, with a calculator today. But at the moment, you can just note that you can use technology. On a spreadsheet, you can use the function equals FTDEV. On a calculator, you can use the S thing that I showed you last time in the stat menu. What do you find if you do that for these data? For March 2014, the mean was about 13 points, the standard deviation was about 13.7 degrees Fahrenheit. I seem to have lost my double yardstick here. There it is over there. Nope, I was deceived. I thought it was a double yardstick. It's a single yardstick. Oh well, it's good enough for today. Standard deviation is about 13.7 degrees Fahrenheit. Note this has units, degrees Fahrenheit. It's a measure of spread. It's not an actual temperature. We're not saying the temperature was 13.7 degrees Fahrenheit. We're saying the spread in temperatures as measured by the standard deviation was about 13.7 degrees Fahrenheit. Don't worry about what the exact number means at the moment. Do notice that for 2015, the standard deviation of 15 degrees Fahrenheit is a little bit bigger than the standard deviation for 2014. That's because, looking at these pictures, there's a little bit more spread in the 2015 graph than in the 2014, especially if you focus again on the main bulk. 20s, 30s, 40s for 2014 being the main bulk, whereas 30s, 40s, 50s, and 60s, in a sense, being the main bulk for 2015. And you have more spread there than you do here. That's an intuitive reason why you get a bigger standard deviation for 2015 than 2014. Again, it doesn't tell you why it's these particular values. Why not 7 and 8 or something like that? We're going to get to that later today, and especially next Tuesday, how to interpret these values for the standard deviation. The main basic conceptual facts to know about means and standard deviation are these. The mean is a measure of central tendency. It is sometimes thought of as a typical value or expected value. In fact, that last phrase, expected value, is an official synonym for the word mean. Whenever somebody in statistics says expected value, it means the same thing as the mean. It is the mean. You shouldn't overinterpret the meaning of those words, though. Just because we say expected value doesn't mean you're going to get a value close to the expected value. We saw that in the data. You're not necessarily close to, for example, 34 degrees Fahrenheit in an arbitrary day on March 2014. So don't overinterpret the meaning of those words. What else is important? The mean is sensitive to outliers. It's not resistant to them. It is affected by them more than the median is, which we will talk about today, the median. So you got a high outlier. It's going to drag the mean high. If it's a really high outlier, it will definitely drag the mean a lot. You think about everybody's income in the US except for billionaires, but then you throw in Bill Gates's income and it skews the mean. It drags it to the right very much so, since he makes, what, $50 billion a year or something. Maybe that's his net worth, I'm not sure. The standard deviation is the measure of spread, central tendency versus spread. Mean measures central tendency, standard deviation measures spread. As a rule of thumb, here's our first basic interpretation of the meaning of the value of standard deviation. As a rule of thumb, most data values lie within 2 standard deviations of the mean. The distance between the mean on a number line and most values in the data is typically less than 2 standard deviations. If that distance is 2 standard deviations, and this distance over here is 2 standard deviations, then most of the data values will lie between these 2 numbers that are within a distance of 2 standard deviations from the mean. That's a rule of thumb. Okay? Most is not a precise word. Okay, so I'm leaving some wiggle room here. Did that work with these data here? Again, the standard deviation for example, 2015 was 15 degrees Fahrenheit. 2 times that is 30. Are most of the data within 30 degrees of the mean, which was 45? 45 minus 30 is 15. Yes, everything except 12 was, over here was within 2 standard deviations of the mean. 45 plus 30 is 75. Yes, 70 got included. Only 12 was not within 2 standard deviations of the mean for 2015. So the rule of thumb worked pretty well there. The standard deviation, just like the mean, is also sensitive to outliers. It is not resistant to them. Those 2 phrases, by the way, mean the same thing. Sensitive to outliers and not resistant means they are affected by outliers. I could use either one of those phrases. It is certainly more resistant than the range, however. The range is the maximum minus the minimum. The maximum could be an outlier. Okay, you change that, it's going to greatly affect the mean, or excuse me, the range. It will also affect the standard deviation, but not as much. Something called the interquartile range, which we'll look at today, is definitely more resistant to outliers. It's less sensitive to them. Got those words? Sensitive, not resistant means greatly affected by outliers. Not sensitive or resistant means not so affected by outliers. Okay. These are all things that could be on quizzes, maybe next Tuesday, maybe next Thursday as well. And maybe even on future quizzes a couple weeks from now, okay? Because these quizzes are cumulative. All right? It is important to make sure you look at graphs first. That's something the book emphasizes as a philosophy. Don't just do computations, especially not first, and then don't make any graphs. It is a good idea to make graphs first, as long as you make them accurately and appropriately. And then based on your graphs, that gives you expectations about what you'll probably see with your statistics, like your mean and your standard deviation. Okay? For example, I look at this graph, for example, and I say it looks like the mean, the center's probably in the 30s, and that's true. If I'd gotten the mean in the 50s, I would know something's wrong. Either I made the graph wrong or I did the computation wrong. Can I clarify anything? That's a review, though I certainly spent more time on a lot of this stuff than I did on Tuesday. There's an important visual interpretation of the mean as well. The mean of a data set can be visualized as its center of mass. What does that mean? In essence, if all the data were lined up on a number line that represented a seesaw or teeter-totter, if you prefer, then you put the fulcrum, right, the balance point of the teeter-totter at the center of mass to make it balanced so it stays horizontal. I had a nice demonstration of this that I made on a program that I use called Mathematica that I was going to show you here today, but then I tried opening up Mathematica before class and it wasn't working. So let me try to draw a picture on the board. You've got some data on a number line. There could be repeats, so you might imagine putting a dot for a data point that's a repeat directly above a previous value. Where is the mean? It's the balance point. If you imagine the number line as being a teeter-totter or a seesaw, a really thin one, say, so it's got practically no mass. Of course, such a thing is not possible to make. You want to put the fulcrum at the center of mass to make it balance. I don't know, maybe right about there. And that location would be the value of the mean. If you have an outlier, say a high outlier, the law of the lever says that more greatly affects where to put the fulcrum to make it balance. You've got to shift the fulcrum pretty significantly to the right in that case to make it balance. Light people that are far away from a fulcrum can balance heavy people that are closer. Intuitively, in terms of data, you could think of the lighter person as being, say, 1 dot, and the heavier person as being, say, 2 dots. You've got to put the fulcrum more toward that in that case, if you only have 3 data points. Actually, the law of the lever is a little bit more precise. The product, in this case, of the distance and the weight on both sides must be the same to make it balance. 16 times 40 is the same as 4 times 160. I guess this person should be 4 dots, and this person should be 1 dot. Why is that important? Just to give you an intuition about where the mean is. And also, for example, if you've got a skewed distribution, we're going to talk about density curves a little bit starting today. You've got a skewed distribution like that. These points aren't necessarily outliers, because there might be a bunch of them, but they're further away from sort of the center than these points are. And so they more greatly affect the mean. They skew the mean to the right more than you might think it should be initially by looking at kind of the center or where the peak is. No, I'm going kind of fast. Hope you're able to pay attention okay. Again, if you feel like a certain thing is confusing, you have the benefit of being able to look at it again. Yeah, I was going to do a mathematical demonstration. I'll try to get mathematical working on this so you can see the demonstration next time. Mathematica is related to Wolfram alpha, if you've ever used Wolfram alpha. All right. So mean and standard deviation are examples of statistics, and they describe center and spread. Okay. The other common way of describing center and spread is with, well, first of all, the median to describe the center. And the median along with 4 other numbers to create what's called the 5-number summary to describe spread as well. We can make what are called box plots, also known as box and whisker plots, to see what's going on here. The 5-number summary consists of a data set consists of the following 5 numbers. Okay? Listen carefully. Use your imagination. The minimum, which is the smallest value. The first quartile, also called the 25th percentile, which is at the point where approximately 25% of the data are less than it. A quarter of the data. First quartile, 25th percentile. The median, which is the middle value, or the average of the 2 middle values, 50% of the data are below it. It's also called the 50th percentile, and 50% are above. The third quartile, also called the 75th percentile, at which about 75% of the data are below it and 25% are above. And the maximum, which is the biggest. Those 5 numbers, which we're about to show you and talk about how to calculate, represent something called the 5-number summary. When you graph those in the following kinds of way, you get what's called a box plot or a box and whisker plot. I typically make mine to look like this, though other people don't always make them look like that. Sometimes instead of vertical lines, they put dots. And where are these vertical lines at? This was for the Minneapolis high temperatures in 2014. This vertical line is at the value 3, which was the minimum, lowest high temperature, only 3 degrees Fahrenheit, yikes, in March, amazingly. Yeah, it's cold here. This one, 25, was the first quartile. 25% of the days were less than 25 degrees Fahrenheit for the high. This one, 35 degrees Fahrenheit, was the median, 50th percentile. Approximately half the data are less than 35 for the high. 44 was the third quartile, or 75th percentile. Approximately 75% of the data were less than 44. About 75% of the days had a high less than 44. And 60 was the maximum. What do you see when you see this picture? You also see this box in here, which is why it's called a box plot. The box causes your eye to sort of focus on the middle. The minimum and maximum are greatly affected by outliers. If we didn't have that 3-degree day, and we didn't have any other days below, say, 15 degrees, that minimum could be a lot closer to the first quartile. The box emphasizes that the middle values are kind of more important in terms of describing the distribution. If you look at the box, the first and third quartiles are pretty close in distance, the same distance to the median. The first quartile is 10 units away from the median, and the third quartile is 9 units away. That middle of the data set's basically symmetric. Overall, though, the minimum is further from the median than the maximum is. So overall, there is a slight left skew to the data. Though, in a sense, since it's so affected by this outlier, because the center is so relatively symmetric, you could say this data are relatively symmetric. And we saw that in the stem plot. The distribution looks symmetric, like a bell curve. Okay? So that's what this particular plot is telling you. And again, the box focuses on the most important part of the data. The range, again, is the max minus the min, 60 minus 3, which is 57. There's something called the interquartile range as well. The distance between the quartiles, which is also a measure of spread that's less sensitive to outliers. 44 minus 25, 19 is the interquartile range. The overall range is max minus min. The interquartile range is the third quartile minus the first quartile. And again, that's more robust. It's less sensitive to outliers, more resistant to them. All things that are good to know, okay? And think about as you do the reading and as you work on the problems. Here's the one for 2015. I tried to match the scales up. You can see it's definitely to the right compared to 2014. Not only a higher mean, but also a higher median. It's got a more pronounced left skew because this outlier, the low outlier, is definitely more extreme from the median than the high outlier is, or high value was. It's maybe not so much an outlier. However, the center of the data, focused on the box part, is maybe a little bit right skewed. So in terms of describing this distribution, the box plot doesn't tell you everything. You might describe it in the way that I just described it. There's a slight right skew in the center, and a slight left skew overall. You could do that. You could describe it with those kinds of words. The range is 70 minus 12, which is 58, which was basically equivalent to the range for 2014. The interquartile range is just a little bit bigger. 58 minus 36 is 22, a little bit bigger than the 19 for 2014. So definitely, 2015 was a little bit more spread out, at least in the middle. You want to use those kinds of words, and you want to look for those kinds of words related to center and spread in the reading as well. 2 websites I found this morning to make Boxplot. For plugging in the raw data, meaning the actual data, there's something called Acula? Not sure how to pronounce that. That's a website where you can plug in the raw data and get a box plot. It's not a labeled box plot, so it's not nice that way. It's also vertical, which I don't like as much either. To make a horizontal box plot that's labeled, you can use this website. However, you have to plug in the 5-number summary rather than the raw data, so you have to know the 5-number summary ahead of time. Here's another example that I'm about to show you the raw data for. Unemployment rates. You're going to have a homework problem related to this that's going to be due next Tuesday, and it's going to be an electronic homework problem. For August 2009, that was right after the start of the Great Recession, right? September, October of 2008. Actually, before that even, the Great Recession started. But the stock market kind of crashed in September and October 2008. And in 2009, there were lots of people unemployed. And this is a graph, a box plot for the distribution of unemployment rates by state in August of 2009. What do you see? You see a slight right skewed because the maximum is further from the median than the minimum is. In the center, with the first and third quartiles, there's not much skew. Yeah, that's pretty symmetric in the middle. Overall, it's pretty high, though. These are pretty high unemployment rates. The median is 8.7%. That's a pretty high unemployment rate. Let's look at the raw data for this now. And I want to show you how to make the next thing that we see here called a histogram with these raw data. Oops, I didn't want to open Excel. Have it, I guess. Take a breath. We're about 10 minutes away from quiz time here. You can take a breath to try to refocus. What I've got here is raw data about unemployment rates. Your problem is going to be exercise 1.27 in the text that has percent unemployment rates for August of 2008. Right at the start of the Great Recession, right before the big stock market crash, the unemployment rates for the various states were fairly low, actually, then. But you go exactly 1 year later, August 2009, and look at these unemployment rates. Alabama went from 4.9 up to 10.4. Alabama was the first state. Alaska, yeah, went from 6.9 to 8.3. It jumped higher also, though not as much. Pretty much every state, I believe, had a higher unemployment rate in August 2009 than in August 2008. The stock market crash definitely affected the unemployment rates. I also have, for interest's sake, the unemployment rates from July of 2015, a little more than a month ago. They're back down lower again. Okay? The August 2015 unemployment rates have not been tabulated yet. And actually, these are just preliminary unemployment rates, they're not the final estimates. Say where I got the data from. What are you going to be doing for your electronic portion of your assignment? You're going to be taking these unemployment rates here and making a histogram, which I haven't talked about yet, for those unemployment rates. I will do it right now for August 2009. Okay, you'll do it for August 2008 on your assignment. Got that? August 2008. These are from the text, right here. You'll see it on the text. When I put the assignment up on Moodle, you'll see that I say to do that. So let's do it for 2009. Actually, I had a happy experience this morning in experimenting with this. Google Sheets is better for making histograms than Excel is. You want to make a histogram for August 2009. Let's see. There we go. Go to Insert. This looks different than my computer, so I'm a little worried. Go to Insert Chart after highlighting those data values. Then pick histogram. It's automatically picked here. If it wasn't automatically picked, if it was picked to be this one, then you'd want to pick the histogram. Notice the histogram is a certain kind of bar chart. It's a special kind of bar chart. There's properties I will talk about as we go here. Let's go ahead and insert this. Why can't I scroll? Insert. There it is. So that's pretty easy. You just click on that histogram, but you want to label the graph. You can do advanced edit right here to label this graph. How should you label it? Pay attention. What am I graphing here? This is the biggest point of confusion for people. I'm graphing how many states had each of the various unemployment rates, at least over certain ranges, called bins or classes. You read about histograms, so this should not be completely out of the blue. This first bin or class goes from 3 to 4.5%. These are unemployment rates along the horizontal axis. pay attention to that. These are unemployment rates there. And what's the vertical axis? The vertical axis is the count, which the spreadsheet tells you it's measuring the count. How many states had unemployment rates in these bins? There was evidently one state, the graph goes up to 1, with an unemployment rate between 3 and 4.5% in August of 2009. What about between 4.5 and 6%? The graph goes up to 2. There were 2 states with unemployment rates in that bin, or that range, or that class. Those words are all synonyms. 6 to 7.5%, there were 13. 7.5 to 9%, there were 11 states, etc. The number of states, by the way, should add up to 50. If you add up the heights of all these, it should add up to 50. And what if a state had exactly 6% unemployment? 6.0% say, is it in this bin or that bin? The spreadsheet I found uses the default that it would be in this bin. 6.0 would be included in the bin to the right, not the one to the left. That's the default. Okay? It includes the left endpoint, but not the right. We should edit this histogram, and you should for your assignment. Certainly give it a name that's more descriptive. Histogram for August 2009 unemployment rates. Sounds good to me. You'll have 2008. Then go down and you want to label the horizontal axis. What should I label the horizontal axis with? This is tricky here. Count. Frequency is another word for count. Relative frequency is a percent. Those are percentages. Should I label it with relative frequency? No, with histograms, the horizontal axis gets labeled with the same thing you label the variable with. These are unemployment rates. That's how you want to label it. They are percentages as well. That's assumed. I could put the word percent unemployment rates at the beginning. You can make this bigger if you want, increase the font size. You can label the vertical axis. Click on this, left vertical. How should you label that? The word count is fine. How many states in each bin? Frequency is okay as well. Sometimes, though, you make relative frequencies, percentages. You take these numbers and divide by 50 in this case. 1 divided by 50, for example, is 2%. You could also label the height of that with 2%, though the scale is not set that way. The scale by default is set as a count. I haven't experimented to see if you can set it as a percent yet. Maybe you can't. Okay? Certainly as a minimum, you want to do those things. You can also change what's called